Thank you for tuning in, everyone. This briefing on grid reliability with increasing penetration of wind and solar is hosted by the Four Corners Wind Resource Center. The Four Corners Wind Resource Center is funded by the U.S. Department of Energy and the Utah Office of Energy Development to provide accurate wind energy information and outreach to stakeholders in the Four Corners region. The Resource Center is a partnership between Utah Clean Energy, Interwest Energy Alliance, and Northern Arizona University. Our speaker today is Brian Parsons. Mr. Parsons is a director at the Western Grid Group. Prior to joining Western Grid Group, Brian worked for over 30 years as an engineer and manager at the National Renewable Energy Lab. He led their transmission and grid integration group. Brian has been a longtime participant and advisor to the Utility Variable Generation Integration Group and served as a technical reviewer for numerous utility-sponsored grid studies. Today, Mr. Parsons will discuss grid reliability issues and strategies for integration of variable energy resources while maintaining important reliability. So without further ado, here is Mr. Parsons.
I am a member of the Western Grid Group, and we are a small group of professionals with regulatory and energy office and engineering backgrounds that are, our charge is to accelerate the transition to clean power futures appropriately, economically, and reliably in the Western grid. So with that introduction, let's go ahead and dive in. I thought first I would tell you what the conclusions will be so that you can hopefully have those reinforced as we talk through the slides. I know we have 90 minutes set aside, but I'm hoping there's a lot of time for questions. But the broad answer in the end is that I think everybody has to realize that the reliability concerns are absolutely valid as we go through this grid transition. The transition's already started. We're seeing a lot of, as Sarah shared, wind and solar are coming online very, very rapidly due to the cost declines, due to incentives, due to clean power plan anticipation, due to portfolio standards, due to just plain economics. But in this transition, we need to be mindful of what could happen. The way our grid was designed is not the way the grid's going to be in the future. So business as usual is not going to be adequate. We do need to be mindful and do some planning, do some studies, do some adaptation. But overall, I thought I'd actually read some words that were carefully crafted by some very good technical experts that work for General Electric as part of the Western Wind and Solar Integration Studies that the National Renewable Energy Laboratory ran. And I'll just read that. The Western interconnection can be made to work well with high wind and solar penetrations and substantial coal displacements using good established planning and engineering practices and commercially available technologies. So I think the key points there are that going to a high variable energy resource, if I use that word for high wind and solar together, variable energy resource, weather driven, you can change the way the grid operates, the way you plan, but you've got to do some good work to make this happen. It's not impossible. It's not overly expensive. In fact, there's a lot of work that looks at some very substantial cost savings as part of these transitions. Obviously, you're transitioning to a future where you're not using as much fuel, and it results in lowered pollution, lowered carbon emissions, and all sorts of other benefits potentially from a clean power future, but it does take some work to get there. So just keep in mind as well some of the things that I thought about that you in your roles can do. Support some assessments. You need to be thorough about it. Ensure that when you're looking at the future, that you're looking at the full suite of system-wide technology and institutional practices. If you just look at a future where you're taking out elements like a coal plant, or you're changing the way you might be using a coal plant, you can't just do that in isolation. You've got to look at what you do to adapt this existing system to make it work. And then finally, if we're looking at this from a reliability point of view, let's evaluate the future grid performance against some specific reliability standards. I often hear people with very broad statements say that things are going to be difficult, things are going to be tricky, but I think the follow-up question would be, okay, but does it still work, and are we still meeting our specific reliability standards and moving forward? So this slide is a little bit complex, and I apologize for that. It's kind of the Western Interconnect-wide version, week-long version of the duck curve I'm sure you've heard about, where adding a bunch of wind and solar to the grid operations produces some challenges. And so this top trace, wait a second, both of these plots are products of the NREL study, the Western Wind and Solar Integration Study version 2, which looked at operational simulation of the grid off into the future. And what they were looking at was about a 35% penetration of wind and solar in different ways. I've picked one particular future scenario here where it's a half and half wind and solar, because it's got some good things to think about going forward. And so that top trace is how the utility electric demand over the whole Western Interconnect would be met for a simulated month off into the future. And this was without the renewable penetration. And on that you can see first at the very top part of the trace, load changes during the day, as you know. And utilities are very used to dealing with variable load. They have all sorts of procedures with reserve and dispatch and unit commitment that allow them to be very effective in keeping the power delivery, keeping the lights on, as uncontrollable load does what it does during the day. They can predict load changes based on weather, based on history, based on day of the week. Certainly, they can't control the fact that I'm going to go turn the electric switch on at any given moment, but they know pretty well that I'm going to turn the lights on at night and I'm going to turn them off in the morning, and they know when industrial load goes up and down. But again, that's not 100% known, and so they're used to dealing with variable load. You'll see the kind of traditional thing you've heard about, the nuclear power and the base and the coal power down there in the bottom in the red and the dark gray or black doesn't change very much over the week. That's why they call it base load right now. So if you look now to a higher future, and this is based on a production cost model that minimizes the costs of meeting load throughout the day based on the characteristics of the different generators. And it also takes into account the physical limitations of the generator, whether it can move up and down physically, ramping if you want to talk about it. It takes into account dispatch and cycling. You know, if you turn off a plant, you may have to wait a while before you turn it back on. So these models take into account all these things. And if you look at that trace on the bottom with the wind and solar injected, what we've done there, the blue on the top part of the trace is the wind, and then we've got photovoltaics and CSP, which are now a new part of this future system. And you'll see that the plots look very, very different. And this can be intimidating and perhaps a bit fear-inducing when it comes to having to change the way you're doing things. It's definitely very different. You'll notice that the coal plants now are not necessarily base loaded. This new energy delivery pattern from the coal is physically possible, and we have, in the work, NREL worked very, very hard with GE and some outside consultants that are very, very well versed in the conventional gas and coal industry to try and accurately reflect the capabilities of those plants. And if you're going to cycle a coal plant, you're going to have wear and tear costs, you're going to have changes in efficiency, and all those things are meant to be reflected in these simulations. And that week that we have there, out of 3 years worth of modeling using historic weather patterns from history, but projecting the needs or load off into the future, this is the most challenging week that they came up with when it came to operations. So this is perhaps the week where the operators are pretty wide-eyed and their pulse is up and their blood pressure's high, but it does work.
Brian, I think we have a question here.
Yeah, Brian, this is Artie with the division. Could you talk a little bit about the introduction in the bottom part of the graph on the curtailment?
Sure.
Are those planned curtailments or are those forced?
These are forced. These are essentially a situation where the adaptability of the system was essentially exhausted. If you'll notice right there, between March 29th and March 30th, if you look at the coal plot down there at the bottom, it's dead flat as far as output. And that is reflecting a condition where essentially you have decreased the coal plants to their minimum generation level, and you're because of forecasting and the need for the future, you know that the wind's going to drop off later on, and the solar's, obviously the sun goes down at night. You're saying, you know, I really don't want to turn those coal plants off, but you park them at the minimum generation level. And therefore, any remaining wind and solar that's delivered based on the weather is excess. And so that's what those little dotted traces are. You'll notice that's the part of the week that has the most curtailment. You park the generators at minimum, and you've got, I mean, at that point you can say, I've got excess wind and solar, and that is the reason for that curtailment. Does that answer your question?
Yeah, I guess I don't understand. Is it curtailment of the output from the coal plant, or is it curtailment of load?
This is curtailment of the wind and solar power.
Oh,
so
okay.
Based on the wind and the solar resources at the simulated power plants, the wind and solar power plants, they would have been able to deliver more power than the grid can really accept at this point. And this is kind of the crux of that duck curve problem.
Okay.
We've tried to, I mean, at this point we've shared the power across the footprint, but there are times, honestly, where curtailment of wind and solar is the most economic solution once you've exhausted all other sources of flexibility. And I'll talk a little bit more about that in some other slides in the presentation. But I think that's a really key point. I'm glad you brought it up.
Yeah,
now.
For clarification, I appreciate that.
Yeah, and one of the things I want to point out here too that I'll bring out a little bit further is that during those curtailment periods, there's actually some interesting opportunities that you can do with that those wind and solar power plants. You know, this is essentially reflecting what you would have done if you would have had sort of a must-take situation and you've got this excess power. It's just the most economic way to balance the system, and that's really what the grid operators' main charge is on a daily basis, is you balance the load and the generation instantaneously by tweaking the outputs from different dispatchable power plants. And certainly some of the later things I'm going to talk about are going to reflect some thinking about how you can make wind and solar dispatchable. And so in some ways people talk about curtailment, and curtailment has a bit of a negative connotation to it, because you are essentially throwing away a very clean, zero incremental cost, because there's no fuel, resource. And so that's not exactly the first thing you'd want to do. But if you think about curtailment also as making wind and solar more dispatchable and more controllable, then it has a little bit more of a positive aspect to it that I hope I'll be able to reflect here in some of the later discussion.
So Brian, this is Brandon from WEC. So are you saying that this curtailment did take into account like the ramping constraints like we would see with the duck curve? Or would we expect this curtailment to be worse if we did take into account those ramping constraints?
This has all of the ramping abilities from the gas and other units built into the simulation. So you'll see, as I said, that flat part of the coal, that's parked at minimum generation. We decided not to turn them off because we want to hold that future capability knowing we'd like to use it later. And holding that as an option is a cost-effective thing, and so we've driven the curtailment. And that curtailment is also reflecting, you'll see the solar ramps down there. You know, you've got these blobs of the orange and yellow, the yellow being the photovoltaics, the orange being the concentrating solar power, which can be dispatched and shifted. I think we've got a 4-hour storage window in the CSP plants, and that's why you see that load shifting to a later part of the evening. But you do have the ramping coming about as a result of the changes in the wind and the changes in the solar as the operator tries to balance with gas and other flexible resources. That is fully reflected in the simulation.
And where is this? What is this, the load profile and resource profile? What area of the interconnection is this for?
This is the whole of WEC.
All of WEC, okay.
Yeah. Actually, I have to take that back slightly. If I think about that a little further, the load profile you're seeing here is, I believe it's the West Connect footprint part of WEC. And we can perhaps offline later go back and talk about what that matters, because it's kind of a secondary effect, but it's the broad footprint generally being reflected as far as the capabilities overall when they do the simulation, but I do believe this trace is the West Connect, including California.
Okay, thank you.
All right. Let me go on. We might come back to this slide because there's a lot of cool stuff on this slide. We'll see how it goes here. All right. So on this next slide, this is reflecting a lot of evolving thinking that perhaps the new coin of the realm, and I've heard Steve Berberich from CAISO say this several times, the new coin of the realm is not capacity, it's capability, and it's flexibility. You can see, if you remember from those plots, Brandon pointed out that the need to move up and down is really, really important in this new world. And what the existing generators can do is going to drive a lot of the way the operators perform. And so looking ahead, looking at flexibility and assessing flexibility is going to be a very important factor. And Brandon led a really good analysis that WEC undertook with the Western Interstate Energy Board and E3, looking at flexibility in the WEC world. And this slide, I think, reflects a lot of the kinds of things they examined. There's all sorts of demand side and supply side sources of flexibility. Certainly using what you've got already in the best way is one of the smartest things you can do. There might be a lot of flexibility in the system right now that you may not be accessing due to institutional practices of scheduling and commitment. Generally right now in the Western Interconnect, unit commitment and scheduling are done on a day ahead and then perhaps an hourly block schedule. We don't have to necessarily do it that way. If you've got a gas plant that can be turned on with sort of a 4-hour lead time, then shortening their unit commitment window from a day to 4 hours is physically possible, but you may need to reform some institutions to do that. And certainly within the hour, when you're looking at dispatch, so if you've got a plant already in line, how you turn it up and down, that's dispatch, can be done on a much less than an hourly basis. I mean, you can send a signal to a simple cycle gas plant and vary the output minute to minute. And so if you went to a 5-minute or a 10-minute dispatch environment, then you're taking a lot of advantage of what physical capabilities you've already got. If you look at a broader footprint, right now we've got 38 odd BAs, balancing authorities in the Western Interconnection. Pacific Core East, there in Utah, is one of those balancing authorities. But if you look at broad cooperation across the footprint, sharing resources, sharing reserves, looking at the resource diversity of wind and solar across the broad footprint, sharing those ups and downs in the wind and solar rather than having to balance the ones that are specifically in your footprint with your specific resources, has a lot of advantages. Looking at forecasting, both load and renewable forecasting improvements can really, really help the operator. There's a lot of advances in wind and solar forecasting that are underway right now. And then better use of the existing transmission. And then look at getting some more flexibility. Can you modify existing plants? When you're getting a new plant, can you incent for flexibility rather than just lowest cost of energy when you're looking at new procurements? So demand response is another huge one. I mean, I know many of you were perhaps at the UAE meeting yesterday, and big industrial and commercial loads have the capability to act as active parts of the grid, and they can be financially ahead in many cases by doing that if there's the right setup. You can control loads with dispatch or with automation. Loads can act as reserve resources, and it's very, very interesting. I don't know if you're all aware, but the Texas has its own synchronous grid. Lone Star State, whatever. The Electric Reliability Council of Texas, ERCOT, is a grid operator down there. And in ERCOT, they have allowances where fully half of their reserves can be served by loads. And that is a very cost-effective source of those reserves. So it's an interesting world where that kind of active participation can be very, very advantageous if there's some loads that can voluntarily be reduced or changed in response to some of those more extreme grid events that might be driving some of the needs for holding resources of reserves over a long period of time over the year. The transmission's key, and then storage is also a very key topic these days. Gas flexibility is important. We hear a lot of dialogue about potential storage solutions, and storage is a humongously valuable resource to the grid. I think we need to be mindful of the different characteristics of different types of storage, and we need to be mindful of the costs of storage. I think as a first opportunity, better use of what we've already got, existing pumped hydro storage, perhaps expanding gas storage in certain situations. I'll talk about that a little bit later. And then looking at some thermal storage options. Off into the future, adding more pumped hydro, looking at batteries, compressed air energy storage, plug hybrid electric vehicles. all those things are potentially valuable in these increasing wind and solar futures. But for now, honestly, those are a bit on the outside edge when it comes to cost effectiveness. I mean, battery costs have come down by a factor of 8 to 10 over the past decade, and yet I still think that they're not quite there yet on a cost and performance basis. But we definitely want to keep our eyes on it and looking off into the future. I'm going to move on to the next slide here. Couple of key points I want to draw off these too many words on this slide. When you look at these futures, analyzing these issues is not simple or quick. You've got to do it right, and it's hard. I mean, Brandon, you know how that study went, and this is not something you can do with a spreadsheet necessarily. It's not something you can do very quickly, and so there's a key time lead message to that part of it. Getting the right inputs, there's a lot of people who have looked at these kind of things, but it's not exactly a common skill set out there, and trying to get the right data, trying to get the right way of modeling, and getting some review by the experts in a transparent fashion would be very important. And I hope, Brandon, that I'm not speaking out of line when I say that having a TRC, a technical review committee, was a key part of that WEC flexibility study.
No, definitely not.
So I've already said business as usual. Historic practices and procedures were not designed with these future potential grids in mind, and we need to think about those differently. So, and then finally, the main point I wanted to pull off this slide is when we're thinking about reliability, you can put it into 3 general buckets, and they kind of overlap. But you want to think about resource adequacy. Do I have enough generation off into the future to meet those future loads? And how do I plan for that? When you talk about variable energy resources, it's a little bit different when you look at assessing a measure like an effective load carrying capability than a coal or gas plant, where you're looking at forced outages as being the main driver. With wind and solar, you've got to look at the weather patterns as well and how close those match to the times of highest demand. And then you get into grid operations as a second area of reliability. Now, how on a normal daily basis does the operator balance the load and generation when you now have a bunch of weather-driven resources in the system? You've introduced another source of variability. Before, they were dealing with variability primarily on the load side. Now they've got a little bit more variability, a lot different kind of variability coming from the weather-driven resources. And then finally, the third area of reliability is a little esoteric, and I'm going to dig into this a little bit deeper because it is an area of concern and very valid concern about disturbance response. Basically, if something happens in the grid, and we know stuff happens in the grid, lightning strikes, generator outages, transformer explosions, stuff like that, we want to keep the system together. We don't want to lose load or drop load as a result of these disturbance responses that can be anticipated but are not everyday occurrences. I want to think about that as part of our reliability assessments. Okay. Step back a little and look a little bit about what's happening around us. And this is a really, in my mind, exciting. I mean, I'm here in the Denver metro area, so Xcel is my utility. And you know how it is. Most people love to hate their utility for one reason or another. But I am actually very proud of Xcel's proactivity in looking at wind and solar. And this was a real, to me, sort of an amazing fact that Xcel has had wind provide over half of the power for a whole day. And if you're the operator sitting there where you don't have a switch, you don't have a dial, you don't have a computer control necessarily of the sun shining and the wind blowing, you can imagine when they started seeing this kind of thing, they were a bit white-knuckled. Hopefully now their blood pressure's gone down a little bit after having more experience with this kind of stuff. They've done a lot of things to do with it. But this, to me, is a very, very exciting thing to see. And it does show that it can be reliably met, and obviously they're doing this in the most economical way they can. So this is a little more details on some of the stuff that's been going on with Excel to your east. Right now, on an annual basis, they're getting about a quarter of their power from renewables, and that's growing very, very rapidly. They are ahead of their portfolio standard requirements, and Excel has publicly stated that they are on an acquisition path at this point. They see the production tax credits and other things, and they're saying, you know what, they've done analysis. The last couple of IRPs have said that new wind and increasingly close new solar power is more economic than the average cost of their existing system. So they want to get as much wind and solar now as they can, because it's going to save their customers money, and it's going to increase the shareholders' value by acquiring those resources. And if you think about the white-knuckled operator issue, we talked about, that last slide talked about more than half. They actually had an hour last November where more than 2/3 of their demand was being met by wind. So that is pretty remarkable, and that's definitely some time to think about. To adapt to some of that, one of the things they've done, you know, if you think back to that slide where the coal plants were parked at minimum generation, in Colorado here, during the spring and fall, when demand is low and renewable power, mostly wind at this point, delivery is high, they've done just that. They have parked their coal plants at minimum generation. They've turned back their gas plants that they want to keep online to minimum and kept them for ramp capability. And they have then started to curtail wind, but in a very creative way. It's not just sending a dispatch signal to the wind plant and saying deliver less power, and they can do that. The wind plants then feather the blades on the turbines and reduce output by collecting less than the maximum amount of power they can. But the really neat thing about it is, instead of, so if you've heard the term regulation service, this is the minute-to-minute, second-to-second adaptation of the power output to meet those semi-random fluctuations in load. So that regulation service is normally provided by a gas plant, or maybe at times by a hydro plant. But in Excel right now, during those times when they've turned everything back, they're providing regulation from the wind. So the wind plants are adjusting their power output based on a regulation signal to balance the load. And that's an exciting thing, because that means you're having renewables act as reserve and act as regulating service. It identifies that opportunity I tried to highlight earlier, that it's not just about curtailment. All of a sudden now they are providing a valuable service while they are being curtailed. Couple of the things that are happening, that map on the right is the footprint at this point of a the Mountain West Transmission Group. They're working to form a single tariff area. That'll be very exciting, I think. It says a little bit about planning. It says a little bit about the way the transmission system will be utilized in a more optimum fashion than just a basic bilateral contract-driven way we use transmission right now. On the operations side, we expect this summer that this joint dispatch agreement within their balancing authority with Platte River Power Authority and Black Hills will take effect. That's going to result in a more efficient use of existing capabilities. A while back, this has been a number of years, gosh, maybe a decade now, They went back. Xcel's got a pumped hydro facility here in the mountains west of Denver called Cabin Creek. And that thing was built when we had a nuclear plant here in Colorado, and it was mainly designed to do day-night peak shifting. So you'd run the nuke all out as a base load, and during the day, when the demand was high, you'd let the water run downhill and deliver energy, and during the night, when the demand was lower, you'd use the nuclear and coal power to pump the water back up the hill to be ready for the next day. Well, they retrofit that facility to act to that same regulation, second to second, minute to minute signal. And now, that pump, they've got variable speed pumps that can be switched back and forth between pumping and generating all the time during the day. Very, very advantageous way and cost-effective way to increase the flexibility in their system to accommodate higher penetration of renewables. Several years ago, they did an analysis about gas. And if you think, I'm going to spend a minute on this.
Brian, before you go to that, we have a question in the room?
Certainly.
So hold that thought.
Hi, Brian. Vijay here.
Hi, Vijay.
Question on the Mountain West Transmission Group is, okay, I understand the planning regions and the whole FERC 1000. I understand also there are individual small planning groups that still do local planning. And what I'm confused is this a transmission group that is within the Xcel footprint, like a collaboration of local small PUDs or utilities, or how are they working towards a single tariff? And the related question is, what is the tariff trying to address? Integration fees or ancillary services? Just curious.
Well, I think the main 2 points of the tariff are that it'll eliminate pancaking across this broader footprint. I mean, obviously that purple boundary is broader than Xcel's BA. Xcel's BA is centered in the eastern part of Colorado, and now we've got even that funny little tail off towards Phoenix is Western Area Power Administration. So having a single tariff is going to eliminate pancaking.
So
pancaking of tariffs, which will facilitate sharing of resources across the footprint.
Whom is this transmission group reporting to, or whom directly to FERC? Or, I mean, I'm just...
No, it's a voluntary transmission group, and I don't have, I think at this point it's 11 different transmission owners.
Thank you.
And certainly they're looking to figure if they can expand the footprint, and showing that boundary with Utah was kind of the point of bringing that up today.
Thank you.
That it's an opportunity.
Thanks, Brian.
Okay. All right. Next point is gas storage. In Colorado, if your wind forecast is over-optimistic, they do have a very nice centralized forecasting program. They did an advanced forecasting research and development program with the National Center for Atmospheric Research and the National Renewable Energy Laboratory. And they have one of the nicest forecasting systems for wind and solar in the country, in my opinion. It's nice, integrated with the utility operators, screens. They really do a nice job. But the forecasts are always wrong. Question of how much and how often. But if your wind forecast is over-optimistic and you don't get the wind that you thought you were going to, then they were seeing problems with gas deliverability. When your forecast is too high for wind, you need to turn the gas up, and if you don't have deliverability, then you got a problem. So they said, oh gosh, the best thing we can do probably is increase the front-range gas storage to address those deliverability issues. So it's kind of a creative storage solution. It's not the classic storage solution people think about when they think about batteries or pumped hydro, but it was very, very cost-effective and had all sorts of benefits, including for me as a consumer of gas for heating. They were able to deal with some price arbitrage issues that helped the consumers on the heat side as well, but it was another creative solution. So let me, is there any other questions on areas of this slide? All right.
like
So we've spent a lot of, I'm sorry, go ahead.
No, I said that we're good to go here. Keep going.
Great. So we spent a lot of time talking about some specific examples, and now I'm going to try and go through the slides a touch quicker, but I catch some key points. The North American Electric Reliability Council, or Corporation, sorry, is the reliability entity for North America, and NERC has a reliability definition that talks about adequacy and it talks about security. And these are the things we've touched on before. I want to talk a little bit about N-1 or contingency response. That's this whole disturbance response thing. And what happens when a plant goes offline? Can we keep the balance? Can we come back into balance quickly and not drop a bunch of load? That's really, really important. And NERC is all about this stuff. And they have their specific reliability measures, and they have an evolving essential reliability services working group that is examining these issues for higher penetrations of wind and solar, and they're moving forward in these areas. We're certainly seeing evolving standards, but they are the body that defines the reliability measures, and they are the body that regional reliability authorities are essentially accountable to. So let's dig in just a little bit geeky here. Let's talk about frequency and frequency response, because this is a huge question when it comes to increasing penetration of wind and solar, particularly when people start talking about scenarios where a lot of coal might be offline or might be retired for whatever reason. Clean Power Plan, portfolio standards, decreasing economics, economic viability of older coal plants. And face it, our system right now has some very big anchor coal plants throughout the West. And in many cases, the system's been designed around those coal plants. And so when you change the system, you have to be very mindful of the changes you're making and what that's going to do to this kind of frequency response. And so this plot to the right is kind of a typical situation where you might see some kind of extreme event happen. There might be a tree fall onto a big power line and short it out, or there might be a big generator go offline for whatever reason. The transformer blows up, or there's some controls problems, or whatever other reason you might lose a generator. And our system that is nominally running at 60 hertz, 60 cycles per second, is going to see a change because of that. You no longer have load balance with generation. You've got more load than you've got generation, and what's going to happen is the frequency is going to drop. And I don't know if you can see my cursor there on your screen, but this drop right here is showing what happens when you lose one of those big elements. That's N-1, force contingency loss in the system. And that, because the load and the generation don't balance anymore, you lose that 60 hertz and it starts to drop. Now there's a couple of things that happen here in this first part of the plot. You've got inertia in the system. Inertia literally is the tendency of something that's moving to continue moving. You've got a bunch of these big coal plants that are spinning, and there's a lot of mass inertia in the generators and the motors, and there's also inertia in the motors of load. And so this inertia, if there's a lot of mass spinning, will have a lot to do with how fast this slope drops on the frequency. And, you know, we're looking at a fairly quick time frame. This is a matter of a few seconds right in here after that generator or transmission line is faulted out. And then what happens in this time period, the initial slope here is determined by the inertia. The more big, massive generators that are spinning, the lower the slope of this drop will be. So the next thing that happens in this primary frequency control sort of time frame is governor response. And most fossil generators, thermal generators throughout the United States have the capability to have a governor. And that is essentially meaning that they're not being run necessarily at 100% output. That setback, that headroom, allows you to quickly respond by increasing power during these events where another generator has dropped out. And that governor response is automatic. It does not require a signal from the central control room, from the operators. It's based on the generator actually seeing the change in frequency and, you know, valves opening up in the fuel supply, allowing the power output to rapidly be increased based on the physical capabilities of the generator. And that governor response is a key part of keeping the system together. The next thing that happens, and so this primary frequency control is what's going to arrest the drop right here. And you'll hear people talk about this, another geeky term called the nadir. The lowest frequency you reach is the nadir. And the nadir is really, really important. And you look at it, you're going from 60 hertz to 59.9 here in this plot. In WEC, the thing we really, really want to do is stop this frequency drop below 59.5 hertz, 59.5 hertz. If you look over here, my point is that in WEC, a lot of sub-regional areas have this thing called under-frequency load shedding trigger at 59.5 hertz. And so that means that when you get to 59.5 hertz, all these protection schemes come into utilization, and you start dropping load. And that's what we want to avoid if we possibly can. And you are dropping that load for a good reason. You're trying to protect equipment. You don't want to have damage to generation or load equipment. And so that under-frequency load shedding is to be avoided at all costs. Well, not at all costs. It's to be avoided as much as possible. Stopping this, arresting this before you get there is really, really important. Secondary frequency control is how you come back. And this is where spinning reserve, automatic generation control, signals from the control room to generators that have maybe a gas plant or a hydro plant is running at part load because you just don't need it at that point. It's not necessarily governor response. It might be unit commitment, or excuse me, the ability to ramp up and down, and being able to provide that kind of regulation reserve. You can bring this back with that, and all this is about, this plot is to let you know and maybe learn a little bit about how this frequency response is important and how having those generator characteristics can be really important. So certainly when you're thinking about frequency response and changing the fleet, do you have that primary response? What's the inertial capability of the system? How much governor response do you have if you start turning off coal plants that have been providing it prior to this? How much reserve have you got with the remaining fleet that's been dispatched, that's operating right now? And what can you do with the new system? It's very, very scary to change where these kind of services to provide this response could come from in the future, and it's very important to be mindful of these changes. One of the exciting things that is not broadly known is that the anchor plants is not the only source of these services. And I say inverter-based generation, but I want to be clear that here what I'm really talking about mainly is wind and solar power plants. A coal plant, a gas plant, a hydro plant are what they call synchronous generators. Those generators spin at some multiple of 60 hertz. So when the interconnect-wide speed varies a little bit from that 60 hertz, so does the speed of the generators. on all these synchronous generators, and that's what provides that inertial response. Now, a solar plant and modern wind plants have a lot of power converters and inverters on them that turn direct current power from a solar panel into alternating current for our system. And an opportunity there is that when you've got these inverters, you've got advanced control systems on them, and they can be utilized to provide some of these classical services that came from synchronous generators before. You can get frequency response from inverter-based generation. This is not something that's been done broadly yet, because we haven't necessarily needed it, but we need to start thinking about it now for the future systems. ERCOT, that Texas reliability, the Texas grid operator, and Hydro-Quebec up in Canada are already moving towards this very fast. They are somewhat smaller grids, and they are seeing rapid increases in wind power in their systems, and they have said to themselves, you know what, we can do this, but we need to start building into our interconnection and our power contracts these capabilities, requiring from wind and solar plants. So it's electronics, it's not mechanics. So in some ways, it's definitely increased complexity, but it may be better than synchronous capabilities in some cases because you can actually tune what you need. Think about a curtailed solar plant. Basically, you've told it, let's just have you running at 90% of your maximum output instead of 100%. You can very, very quickly change that back to 100% if you need it. Or if there's, so it's very, very fast-acting frequency response. These are commercially available right now. These are not generally required yet. We ought to start thinking about requiring them. It does mean some business practices and perhaps some standards practices that need to be examined. There's a lot of activity thinking about this right now. There's also another kind of interesting thing that when you think about inertia, I talked about spinning mass. Wind turbines obviously are spinning, so there is physical inertia in the system. Since you've got power converters, you have control over now a rotating mass that can have even better inertial response than a classic synchronous generator, because you can suck it out faster. You can slow this thing faster. It's something that probably would take a good 15, 20 minutes to fully explain, but there is wind inertial options that do not require curtailment. So you don't have to have it delivering less energy. You suck it out faster for a few seconds or for a minute or so as you slow down that wind generator, and then you've got to recharge it, basically. It's almost like spinning storage.
Brian, we have a question.
Certainly.
Hi, Brian. This is Jennifer Gardner. I was just going to ask you if you know anything about the work that California's Smart Inverter Working Group has been doing. It was my understanding that they were looking to apply mandatory requirements for this capability by late 2017. Is that the case? Do you know?
Well, I know they're moving towards that.
Okay.
This is it's an interesting issue on smart inverters. It's one way that you do these controls. So if you wanted these inverter-based generators to do this kind of capability, then those kind of smart inverter standards requiring the capability is a mechanism to get there. Absolutely.
Okay.
One of the interesting points here when you think about this, particularly with solar, is that right now, honestly, most large-scale transmission grid connected solar plants already have these capabilities in their controls. The complexity comes in if you think about all the people in California and other parts of the Southwest that are putting PV on their rooftops on the distribution side. Now, those inverters tend to be a little bit less advanced right now. A standard inverter doesn't necessarily have these control capabilities built into it. Adding the capabilities is not extremely expensive, but it's not standard practice right now. And so the Smart Inverter Work Group in California, the Rule 21, things that are happening in Hawaii are often aimed at advanced capabilities from distributed rooftop PV, because as the penetration of those systems goes up, taking advantage of that capability for that resource could become very, very important and could be very economical, but it does require some anticipation. And I think that's what a lot of those efforts are working towards.
Okay, thank you. And Brian, I have sort of a follow-up question. I'm just trying to make sure I understand this. So, and if I get the terms wrong, just correct me. So, I always hear that we need a certain amount of spinning reserve. So are you saying that, for instance, solar or wind could serve as spinning reserves by just backing off a little bit and having headroom to move up? Is that what a spinning reserve is? And is that what you're saying, that
yes,
renewables can act as
absolutely.
spinning reserves for renewables?
Yes. Yes.
Okay.
Spinning reserves are what takes place here during a rebound period. You're using the active signal from the control room to ramp up output on generators that have that capability, because they're not running at 100%. And that can be from wind or solar or gas or hydro or even coal. They have ramp capability if they're turned down to less than maximum. Ramping and automatic generation control also are used on a daily basis to balance. That's that second-to-second balancing. It's not just for these disturbance events. In fact, it's more often utilized for just day-to-day balancing. And that's really what I was trying to explain about Excel, is they're using that wind and solar for that second-to-second, minute-to-minute balancing as the wind is curtailed and everything else is parked at minimum generation. So they're using the wind as spinning reserve, and they're using that as their regulation service. So it's a very exciting new way to think about curtailed wind and solar. Okay, so last point on this slide, and then we'll move along. Right now, our system seems to be run just fine with about 30% of our online megawatts having the governor control. So governor response activated. So if you look off into the future, you retire a whole bunch of fossil plants and you're running on a system that's got half or more of the energy coming from wind and solar, then you have to start thinking about, okay, if we're going to have 30% of our capacity needing to have that governor response, then let's think about how we do that. The remaining conventional generators can do it. Wind and solar can do it. Having the capability, as Jennifer brought up, could be very important to know. But longer term, we need to think about how we can access the best, most cost-effective way to do it. And so people are starting to think about, how do we design a market, or how do we economically optimize the best sources for this kind of response? Capability matters. How you actually get it and how you compensate for it, is kind of the next steps. Okay. Disturbance response, we've already talked about frequency response. It's an interconnect-wide issue. We've talked about N-1. In WEC, our N-1 design event is the loss of 2 of the Palo Verde nuclear units in California, so basically dropping 2 3/4 of a gigawatt of power in a very short time. Can we hold it together? And the challenge for the clean future is, the worst case is when you've got light spring load with lots of wind and solar and not very much load. So that's just kind of keep in your head what the frequency response challenges is for the future. There's another part about disturbance response that gets even geekier, and that's transient stability. This is voltage stability in weaker portions of the grid. We'll just say portions where there might be lots of generation and not much load and very, very long transmission lines perhaps. And these are all local issues, more localized when you have these kind of disturbances. And in this case, location of the generators absolutely matters. Whereas with frequency response, the location of the generators is not as important. Frequency is an interconnect-wide phenomenon. Transient stability is more local, so location matters. So if you retire a coal plant that the system's been designed around, then you've got to think about your replacement power, where it's put. It doesn't matter so much, the key point here is it doesn't matter so much if the replacement power is gas or wind or solar. What really matters is where it's located on your transmission system and what capability it's got for voltage and bar support. Any of those generators can provide it. The location really matters. And there's a couple examples there of some of the big design events for transient stability for the Western Interconnect. And the takeaway point, if you have to remember anything on transient stability, is that the worst case for renewables is high summer load, when you've got very heavy path loading on the transmission lines, and then you have a fault event. That path loading and high summer load is way different than the worst case for renewables on frequency, when you've got light spring load and lots of the conventional generators turned off. So these are the kind of engineering nuances that really matter when looking off into the future. And it shows the complexity of trying to deal with these, keeping reliability off into the future. Can be done though. Disturbance response, there's a whole bunch of conventional solutions we've done for years. I mean, these things have been around forever. They've gotten more advanced in ways, but you know, capacitors, series compensation, static and dynamic bar controllers, transmission reinforcements, all sort of classical responses to these kinds of issues in designing a system. We've talked about disturbance response with high wind and solar, and this really tells you the results from a very key set of studies called the Western Wind and Solar Integration Studies 3 and 3A. Again, General Electric and NREL and the Department of Energy examining those futures, taking some of those challenging times when you've got for frequency response, you've got the light spring load and heavy wind and solar response, and they've shown that you can stay within the reliability standards. You can maintain frequency above that 59.5 hertz, where the emergency tripping starts to happen, where load shedding starts to happen. We can maintain that. Talk a little bit about the new evolving frequency response obligation standards from NERC being able to be met in these futures. And perhaps the thing I should jump right to that I find perhaps most revealing is that reduction in coal commitment. For these simulations, these are snapshot disturbance response simulations in time. They're not looking at the full year. They've taken the worst case and said, what happens if a fault happened when we had the most vulnerable set of generators dispatched? And so in these cases, coal commitment and coal retirement are essentially equivalent. The coal's turned off. So 80% reduction from our current system operating was acceptable in WEC for these disturbance response criteria. If you went up to a 90% reduction in coal commitment, all of a sudden you're seeing problems. You weren't meeting the reliability standards. But they were able to remediate that with these things called synchronous condensers, which are essentially spinning generators that do not have a fuel source on them. We can talk about synchronous condensers. You can actually make a coal plant into a synchronous condenser by cutting off the turbines. Same thing with gas. Synchronous condensers have been around for a while, but the amazing thing to me was just that if you went to this extreme case where all of a sudden you have 90% of today's coal commitments gone, you can still have a stable, reliable system by adding, I'll just add my own modifier, a mere 3 synchronous condensers strategically placed throughout the Western Interconnect. To me, that's a very, very surprising result, as a very, very cost-effective result, it's not drastic, I guess is the emphasis here. It's not a drastic solution is required in those kind of situations.
So Brian, I have a question. This is WEC-wide that you would
Yes.
need only three, and how much does one cost? And then do they use fuel to keep spinning, or how do they spin?
They spin by, the only thing you've got to do to keep a synchronous condenser going is make up a very, very small amount of losses. I mean, you got something spinning, you've got bearings, you've got electric flux, you've got all this stuff, and so you've got a little bit of loss. And so to keep these things running, you basically got to charge them with a little bit of power from the rest of the system. They don't have a fuel source of their own. So they are a little bit of a draw from the system, not very much. So they don't have a fuel source. I've got a slide here I'll jump to about cost. So let's go ahead and catch one quick point here and then and hold me to it. I'll jump to the cost of a synchronous condenser. Rooftop PV, you've heard a lot about, you've probably heard about Germany. You've probably heard about Hawaii, where they're really, really worried about rooftop PV causing problems in the system. And we've got this whole thing in this country where there's this thing called the IEEE 1547 standard. This is a electrical mechanical body that works to come up with standards to make the electric system work well. And from a distribution system point of view, you can think about this changing world where all of a sudden, the distribution system downstream of the transformer in your neighborhood was not designed to have power sources on it. They didn't anticipate rooftop PV or other distributed generation sources being on the distribution system. And the last thing they want to happen is, let's say there's a problem out on their distribution system, and they send out a lineman to work on the line. They don't want that lineman to get hurt or electrocuted, essentially, if there's power feeding into the grid and he thinks it's disconnected. He thinks it's a non-active power line. And so safety is paramount in the electric system. It's a huge, huge thing to be safe. And so IEEE 1547 standard was designed to deal with that safety issue. What it basically says is if the grid goes down, that all distributed generators should disconnect so that they can safely deal with remediating the problem. The problem is that if you get a high penetration of wind of these rooftop PVs on the distribution system like they were getting in Germany and Hawaii, if these things all trip off at the same time, you've made the ability for the system to recover even worse. You know, we talked about that highest contingency event being Palo Verde tripping. It's gotten to the point in Germany where synchronous tripping of rooftop PV is the highest contingency event in their system. So that is worse than their biggest nuke or biggest coal or biggest transmission line fault. That is a big problem. That is a big, big problem. And if you think about a cascading event, let's say Palo Verde tripped. And all of a sudden, all these inverters saw that, and they tripped too. The future in California, all of a sudden, your contingency event might be 2 to 3 times larger than Palo Verde because you've got synchronous tripping of all that PV. And so part of the rooftop tripping problem, you probably heard ride-through characteristics and ride-through standards. And so there's a fix underway to change the ride-through standard. So for safety reasons, you still want to have that de-energized, but you want to not necessarily trip the coordination simultaneously. And some of these California Rule 21 smart inverter standards, there's a revision of 1547 underway. It absolutely has to be addressed. Absolutely has to be addressed as we go forward. It is being addressed. Honestly, it's glacially slow, but we're getting there. The nice thing is that in most places, rooftop PV and the pace of these revisions, it looks like it's going to be okay. It's been a bit of a freak out for some of the people up to this point, but until these revisions did get underway. But let's go back to let's stop a second. Is there any questions about that synchronous tripping issue in distributed PV?
So I have a question about that, Brian. So I've been reading about many of the inverters, and they say that they're already ready, and I forget what exactly it says for like the Hawaii requirements or the California requirements. So it seems like the inverters are already incorporating those technologies, but it's just not, they're not enabling that part of the inverter until they take care of the IEEE standard.
Yes, I think that most inverters that are going in now do have the capability. I don't know the percentage. There's some that don't. Mm-hmm. And it's kind of interesting. This story can be, this is one of those anecdotal things that have all sorts of interesting aspects to it. Germany, they recognized the problem. And they said, uh-oh, we got a problem. Well, these were older inverters. Mm-hmm. They actually had to go out and manually retrofit every inverter on every rooftop PV system in Germany. Enormously expensive, enormously stupid to have to do that. This was an anticipatable problem. Hindsight, I guess, is 2020. But it costs millions of dollars. Literally more than $1,000 on average per inverter to go fix this. Boy, do we not want that to happen in the United States. So the capability is there now in most of these inverters. Now the cool thing in Hawaii, this is the good news story rather than the oh crap story of Germany. Hawaii has these higher penetrations hitting as well. And one particular inverter manufacturer, I think, has about 85% of the inverters in California, or excuse me, in Hawaii on the rooftop PV. And there was a guy on his PC in the headquarters of this inverter manufacturer who was able to, with his computer, change the settings of those inverters in Hawaii. A little bit of software, a little bit of programming, a little bit of simulation, and he just pressed his keyboard and fixed the Germany problem in Hawaii. Not thousands of dollars, millions of dollars overall, wasn't more than $1,000 per rooftop system. So this is why having the capability and these smart inverter standards and this IEEE fix are so, so important. Does that help, Sarah?
Yeah, that helps. And Brian, I just want to say this stuff is fascinating because we've already gone through, we only have 15 minutes left. So whatever you think is most important to cover in the last 15 minutes, unless you think you can make it through your slides. But if not,
I think we've got most of it.
Okay.
And so yeah, I think you're right, Sarah. And I do want to open it up to and get some additional thoughts. My slides are going to be available to you. If there's any follow-up later, I got a whole bunch of resources at the end, references, studies, that kind of thing. So please, chime in if you've got a burning question here in our last remaining minutes.
We have another question. Oops, was there one on the phone? No.
Yeah, I have a question, Brian. I don't know.
Why don't you come up to the table?
This is Peter Ashcroft in Utah, and I don't know if you're the person to answer the question, but when you talked about the retrofit, the expensive retrofit in Germany, is there any concern that we might be installing technology now in Utah that at some future point there would be a need to retrofit? Is there comfort that the capabilities of current inverters being installed will really get us through future situations and future requirements? I don't know if that's a question.
That's a good question. I don't know the local specifics of what capabilities are in the systems that are being installed in Utah. I think it's definitely worth some further inquiry. Generally, I think that the big concerns are for rapidly expanding deployments. You know, California's already seeing it. Arizona's already seeing it. Utah and Colorado are starting to see it. In general, many of these, and this applies to both the bulk system and the distributed side, some of these capabilities may not be there in some of the older plants or some of the historic plants or even some of the ones that are going in currently. But the big issue is going to be anticipating what's going to happen as we get more and more of this stuff. The problem is going to get more and more pronounced. And you know, most assessments show that if you get on it quick, don't just sit on your laurels, but get on it quick and anticipate and study, that requiring the capability or accessing the capability with future plants is probably going to be plenty. You know, as I said, this frequency response, for example, to go back and emphasize the point, you only need 30% of the online generation to have the capability to do it. So you don't have to access everybody, but since the capability, adding the capability is cheap, why not? There's a whole notice of inquiry that was just closed a week or so ago at FERC, looking at fast frequency response, and should we require all generators? Should we have to retrofit old generators, or you know, those kind of questions? And you know, my sense of it is that you don't have to retrofit. You don't have to have absolutely everybody, but let's get on it. Let's start thinking about the future and anticipating the most cost-effective thing, and maybe a little bit of study ahead of time, maybe a little bit of incremental price. You know, just to give you an idea, I think that adding the capability to a modern wind plant, you know, it's probably already there. You're activating the controls, 1 or 2% more in cost, capital cost up front. So it's a big deal as far as dollars, and retrofitting for existing contracts is a big deal. But you probably, you know, anticipation, get on it now. You may not have to have the ones necessarily. I don't know if Utah's, you know, staring down a big problem, but my guess is probably not yet. But get on it now is a good thing.
And I'll add that most of the inverters, or a good percentage, are the Enphase, which have the capability. But I think that's good to think about whether or not we should have think about requirements or, yeah, standard. And Jennifer has a question.
Yeah, Brian, you brought up an interesting point regarding the FERC notice of inquiry. So it sounds like FERC is looking into the question of whether we should require all generators to provide this primary frequency response capability. At the UAE meeting yesterday, we heard a presentation from Maury Galbraith with Western Interstate Energy Board. He said that they submitted comments to NERC on that very issue, and based on some analysis that they had done with GE and I'm forgetting who else, they had found out that you actually only need 30% of generators online to provide that frequency response at any one time. And I'm curious if you have the knowledge or the background to provide a comment on that, because that's a pretty big difference. If FERC's looking at 100% and this other organization saying, nope, you actually only need 30%.
Yes, that's exactly the 30% number I was referring to.
Oh, okay.
That's a fairly consistent set of analyses out there. It's not widespread yet as far as, you know, deep dives on that, but it seems to be a consistent number that you absolutely do not need every generator to have the capability enabled at that particular instance. So yes, you certainly need to think about what makes sense. And that's kind of this retrofit question. If you've got a historic generator set that doesn't necessarily have the capability right now, do you really need to go back and have them do that or not? Maybe not. And there's definitely a healthy technical debate about what makes the most sense going off into the future. Do we require the capability on every new generator, or are there some generators that can provide that easier than others or more economically than others? And, you know, this idea that the wind and solar, for some of these capabilities, for many of these capabilities, have to be curtailed. So you're throwing away free clean energy, nearly free clean energy. So is that the smartest thing? Well, okay, yes. But then you start thinking about a future where during certain, I mean, California now is looking at 50% renewables on an annual basis. So if you look at what that means on an instantaneous basis, to average 50%, there's going to be times, like in Colorado, we're already seeing 2/3 of our power coming from renewables right now. So looking off into the future, you can certainly see a point. I mean, we've already reached that point in time where less than 30% of their online generation is coming from non-renewable sources. And therefore, they've already, if those renewable sources don't have those capabilities, they've already tripped that 30% rough rule. So requiring the capability is a big debate. But I think it's one of those things that careful, considered analysis is really appropriate right now.
Great, thank you.
Okay, there's your synchronous condenser costs. Really cheap. You can convert an existing plant. You can get a new one. They're even talking in California about putting a clutch on a gas generator, which essentially means you can disconnect the turbine and turn a gas plant into a synchronous condensers when you need it, when you don't need the gas as a generator. Storage and demand response are huge disturbance response additional solutions that are not currently considered in the existing system. So lots of different sources. And I think we're getting awfully close at this point. Let me see. You can go and see, we've already talked a little bit about what there's high value from. This is definitely worth a minute or so. When we look at the operations of the grid, big regional cooperation is one of the lowest hanging fruit when you look at how you can best accommodate these penetrations of wind and solar economically. Sharing the resources across the footprint. Sun goes down in California at a different time than the sun goes down in Utah and Colorado. Wind blows at different times. Demand peaks are at different times. So broad regional grid cooperation is a high value mitigation measure in the future that's relatively inexpensive. Now, institutionally, it can be really challenging to get there, for sure. Couple other the big ones. I already talked about the shorter unit commitment and dispatch windows. If I had to pick a 1 and 2, it would be regional grid cooperation and then shorter unit commitment and dispatch windows. Big deals. More operational results. Let me just jump to the end. There's a report that talks about this that the Western Governors Association did, looking at the feasibility of these higher penetrations in the future, drawing on some of the NREL studies. And the cool thing, as regulators and as support and energy staff, this identifies the barriers and institutional challenges and possible solutions. So this is a really good resource for the people in the room, I think. So if you're interested in finding out what some of the key actions could be. And with that, I think I ought to jump to questions as we go forward. There's a whole bunch of resources at the end of my work that look at the different studies. California's done a low carbon grid study that looks at a 50% carbon reduction in California, but it does simulate the whole of WEC, and it shows the value to California and the high need for California to expand regional cooperation. I think this has a lot of bearing on the energy imbalance market and the expansion of the regional system operator. All of that is actually doing what these studies have shown, that there's a high value to that kind of broad cooperation. Yeah, and if staff is interested in learning more, I really would just highlight one more potential resource. Both Vijay and Brandon and WEC have been active in the Utility Variable Generation Integration Group. This group has been around forever, and it's a peer-to-peer utility geek forum for sharing solutions and problems in this whole future of high penetration wind and solar. So I would highly recommend, perusing your website, considering sending key technical staff some of their meetings and workshops. It's a great place to sit down and talk turkey with your peers about what they've done, be it Excel or California or ERCOT, or even if it's other places where they're not quite as far along in the penetration levels, and addressing what they're going to do next and what their most cost-effective solutions and what they're considering is going to be. Really, really valuable for them.
Hey Brian, this is Jennifer. Who hosts that that group that you were just talking about? Is that a WEC hosted group or is it an independent group?
Yeah, no, the UVIG is an independent group. It's a 501c3, non-lobbying, nonprofit, and the members are utilities. Every grid operator, every ISO in the United States in the organized markets is a participant. Most of the other utilities, WEC is a member, Pacificor is a member, Excel is a member, a very active place. But I guess part of the opportunity is that if you know of particular people who could benefit from going, that the depth of UVIG into each of those organizations tends to be rather thin. Thankfully, WEC is pretty active with Brandon and VJ, but if I had to go back and say, from Excel, it's 3 people, 4 people deep who've been participating, and they've been great. So if there's somebody new or somebody who, in an emerging capacity, is wrestling with these issues, it's a great resource. The dues for UVIG are very, very low on a relative basis, and getting to their meetings and listening is the point. It's got an independent board of directors elected by the members that include investor-owned utilities, public utilities, both municipals and customer-owned public utilities, as well as some representation from the industry. General Electric, the analysis team has got a member on the board of directors now, as does a gentleman named Mark Holstrom, who's on the board of directors as well from NextEra.